Hi everyone. Good morning. Currently it's 7 a.m. for me, and it's very early, so good morning, and also good afternoon or good evening to those in other time zones. My name is Dipti Mahamuni, and I'm currently studying computer science at Arizona State University. And today I'll be presenting a comparative framework for evaluating consensus algorithms for blockchain. So to begin with, the core of a blockchain protocol is a consensus algorithm that it depends on. And there's a plethora of these consensus algorithms. Each of these consensus algorithms behaves differently regarding different evaluation criteria. So regarding security, performance, cost, or latency, each of these consensus algorithms behave differently. So what I found was that there wasn't a holistic framework to evaluate these consensus algorithms based on these few criteria. So in this talk, I hope to present a definitive framework to evaluate these consensus algorithms. Now, before I go into more detail about the paper, let me explain what these consensus algorithms are and why they're needed. So if you take a look at a blockchain or a decentralized ledger, it's all about a set of decentralized nodes executing transactions and storing the results. However, each of these decentralized nodes should have the same information. This means that they should be looking at the same piece of information, which is a transaction, at the same time, and they should make their decision in unison. So the system will only work if all of the nodes are receiving the transaction information in the same order and at the same time. Now, if we assume that all of these nodes are honest, which is not always necessarily the case, the problem is that each of these nodes across the globe have their own timestamps or clocks, which aren't synchronized. The second problem is that there's no guarantee that all of the nodes will receive the same information in the same order and at the same time. So if you take a look at the picture on the right, you see that there are 4 nodes and there's 3 transactions. So in the picture, node 1 has received the transactions in the order A, B, C. Node 2 has received the transactions in the order C, A, B. Node 3 has received the transactions in the order B, C, A, and node 4 received transactions in the order A, C, and B. Now, these nodes, all 4 of these nodes, need to agree on which transaction to process and in which order they need to be processed. But this doesn't necessarily mean that the transactions need to be processed in the order that they came in or in the order A, B, C, because it's alphabetical. Any arbitrary order, such as A, C, B, is okay as long as all of the 4 nodes agree that the order that they'll process the transactions in is ACB in that order. So if the nodes just process the transactions in the order that they received them in, it won't lead to a successful blockchain because they'll reach different conclusions. So all of the nodes need to agree on which transactions to execute and in which order. So this is where consensus algorithms come into play. So going back to assuming that all of the nodes are honest, that's not always true. Some nodes can be malicious and they can send bad or wrong information on the network. They can even decide to hold off on sending information to the network. And this is what's classically known as the Byzantine generals problem in computer science literature. So here's a picture that describes the Byzantine generals problem. In the box on the left, there's a kingdom with the king sitting inside of it. And the Byzantine army is surrounding the kingdom and they want to attack it. So the only way that the king can be defeated is if each army member agrees on exactly what to do and they launch their attack at the same time. However, since the army is scattered around the kingdom, the general cannot properly give instructions for a coordinated attack. So the way that the general can communicate with the rest of the army is through messages sent by messengers. However, the box on the right shows that some of these messengers could actually be traitors who were working for the king. But now, what would happen if they sent a message opposite of what the general wanted to send? If the general wanted to send an attack signal, the messengers could send a retreat signal. This means that the army wouldn't be able to coordinate their attack. This is similar to how the nodes need to be coordinated on a blockchain network, hence why consensus algorithms are needed. They help to ensure that there's only a single version of the truth. So there are a couple of common consensus algorithms that make this happen. The first being proof of work. Proof of work involves miners, and these are like Bitcoin miners. And they solve a cryptographic puzzle. So essentially, all of the transactions are placed on a block, and they have to try to find the hash of the block below a certain minimum number. And this hash can only be found through repetitive trial and error. So the way that this process works is that a random nonce is generated, the hash is calculated, and is checked if it's below a certain threshold. If the hash doesn't meet the conditions, the whole process repeats again and again until it's correct. So most of these attempts are unsuccessful, but the process is repeated until a nonce producing the correct hash is found. And for that reason, this consensus algorithm consumes a lot of energy because of the enormous amount of computation needed with the trial and error associated with finding the correct hash. It also takes a significant amount of time. So although it sounds expensive, this algorithm makes it incredibly hard to cheat the system or for a malicious actor to manipulate the blockchain. This is because even the malicious actor has to perform all of the time-consuming calculations while simultaneously racing against all of the other miners in the world. So that means that they would need more compute power than the rest of the world, which makes it very difficult to manipulate the system. And Bitcoin is an example that works on this consensus algorithm. Now, since proof of work consumes a lot of energy and it's very time consuming, another consensus algorithm called proof of stake was developed. In this algorithm, the miners must stake their own money in order to gain the privilege of becoming a miner. So from the pool of miners who have staked their money, one of them is chosen at random to be the leader. The leader gets to pick a transaction and write the block on the blockchain. After this leader gets their turn, the next leader is picked, and so on and so forth. Now, these leaders earn money in return for producing that block. But what exactly incentivizes these leaders to be honest? There are many other nodes that can easily validate the work of the leader node. And if they can prove that the leader cheated, then the stake that the leader had can get confiscated. And this process is called slashing. And the money that was in the leader's stake gets slashed as a consequence of being dishonest. So this prevents leaders from cheating and doing bad things. And this algorithm is obviously cheaper as compared to proof of work because it's not as time or energy consuming. However, it did allow for some novel attacks to be introduced that it is vulnerable to. Now, both of the algorithms that I just talked about are good and bad in their own ways. But how do you really compare them, and on what criteria do you compare them? That's where the framework that I created comes in, based on 5 evaluation criteria. So the first evaluation criteria that I looked at was security. So first up, the Sybil attack is when a malicious entity gains influence over the blockchain by creating fake identities, devices, IP addresses, or virtual machines. So the current set of consensus algorithms such as proof of work and proof of stake are resistant to the Sybil attack to some degree. This means that as long as a malicious actor cannot get control over a large proportion of nodes, hashing power, or stake, these consensus algorithms are safe. However, there's still a possibility that these protocols could fall victim to the Sybil attack because there is a slim chance that the malicious actor can end up getting control of that. Second are eclipse attacks, which are when an honest node is prevented from getting the current information on the blockchain by surrounding it by malicious peers. So, like with the Sybil attack, the current set of consensus algorithms like proof of work and proof of stake are also resistant to this attack. Again, if a malicious actor is able to gain control over a large proportion of the node's hashing power or the stake, these protocols are at risk. Third are 51% attacks. So 51% attacks are when an attacker can control 51% of the stake or 51% of the hashing power of the network. So both the proof of work and proof of stake algorithms are vulnerable to this type of attack. In fact, the proof of stake algorithm and its variations, such as basic proof of stake, delegated proof of stake, and least proof of stake, can also fall victim to the 51% attack. Security against this attack is actually difficult because the weaknesses are inherited from the consensus algorithms themselves. Therefore, although it's hard to protect from this attack, detecting the attack can be made easier by enabling transparency for which of the 51% of the nodes are in agreement while committing fraud together. Fourth are internet-based attacks. So some examples of internet-based attacks are routing attacks and BGP hijacking attacks, which divert traffic away from genuine nodes on the blockchain. And another example of internet-based attacks are DDoS attacks, which can overwhelm the blockchain nodes. So with routing attacks and BGP hijacking attacks, attackers can then prevent the publication of honest blocks and they can push their own malicious blocks onto the network. And from there, they can also create forks and start double spend attacks. So the earliest proof of work algorithm was designed to solve these problems, but since then there have been several successful attacks on it. So while an internet-based attack is underway, the consensus algorithm should make sure that attackers can never compromise the integrity of the ledger. So in this way, the leaderless DAG-based algorithms end up performing better than leader-based algorithms do. The fifth sub-criteria in this is double spend attacks, which is when malicious actors use race conditions or time to finality to their advantage to execute a transaction multiple times. So again, proof of work and proof of stake are two algorithms that are vulnerable to double spend attacks. And the reason that proof of stake algorithms are vulnerable are due to a problem called nothing at stake, which is when a malicious node has nothing in its stake and therefore nothing to lose or nothing to counteract its malicious actions. A malicious actor with nothing in his stake is not afraid of getting slashed. Moving on, the next evaluation criteria I considered was decentralization. The fundamental concept of blockchain is decentralization. And one of the core principles of Bitcoin was democratizing control to the hands of everyone. Decentralization is important because it helps to build trust in the network and it prevents the network from being easily manipulated by just a single organization. So here are the 5 factors that affect decentralization. First of all, we have decentralization with scale. So the scalability of the nodes that run the ledger is really important to the network because as the number of nodes on the network increase, the trustworthiness of the network grows as well. Also, as you increase the number of nodes, the degree of decentralization increases as well. Secondly, we have geographical distribution. So geographical distribution doesn't exactly concern the consensus algorithm directly, but it is unfavorable if the protocol encourages nodes to be concentrated in a single country or a single geographic area. So one example of this is the disproportionate amount of Bitcoin that's mined out of a select few countries due to their cheap electricity prices. And this helps them because the proof of work algorithm is very power hungry, so they don't have to pay as much for electricity. Third is permissionless operation. So permissionless operation is preferred in order for anybody in the world to validate the transactions on a blockchain without having to explicitly ask for permission from the nodes that are already there. Fourth is having open source code. The code of consensus algorithms should be open source so that engineers are able to find and fix any security vulnerabilities. And also, having the code be open sourced eliminates any overdependence on just a few smart engineers. Fifth is specialized hardware. Some consensus algorithms need specialized hardware to run, such as FPGAs or GPUs. Consensus algorithms that are based on proof of elapsed time rely on specialized hardware that's only found on Intel CPUs that support the Trusted Execution Environment, or TEE. Another example of requiring specialized hardware is Ethereum mining, which is accelerated with the help of GPUs. The need for specialized hardware reduces equality and therefore makes things more centralized. The next evaluation criteria that I looked at was scalability. So right now, about 10 transactions are happening today on Bitcoin every second. If you look at Visa, on the other hand, it does 8 to 10,000 transactions per second. However, our goal is to have the world's transactions on a ledger. So to handle this, Bitcoin would have to scale 1,000 times. And in order to scale so much, the time and the energy needed would be enormous. So how can that problem be solved? First, I took a look at energy consumption. The proof of work algorithm is very power hungry due to the massive amount of computational power needed just to add a block to the blockchain. And this computational power requires an excessive amount of energy usage. Algorithms based on proof of stake or proof of burn, however, they manage to reduce this computational power that's needed, therefore also reducing their energy consumption. So a good consensus algorithm should consume the minimum energy required per transaction. Second is finality. So the time to finality of a transaction is the time from when the transaction is submitted to the network to the time the transaction is recorded on the blockchain. So since the proof of stake algorithms spend less time in complicated computations, block finality is faster for proof of stake than it is for proof of work algorithms. Finality also has practical applications, such as the processing of credit card transactions, because you want it to be fast. Third is throughput. Throughput is important for scalability, and proof of work algorithms cannot handle throughput that well due to its time-consuming nature. So without the right hardware for proof of work, solving the hash would take even longer, therefore reducing the transaction processing rate and the throughput. Proof of stake algorithms are good at handling throughput for the same reason that proof of work algorithms aren't. This means that they reduce the complicated computations that are so time consuming that it affects their throughput. Next, I looked at governance. So first of all, forks are bad for the network. They can create multiple sources of truth and in return, they can reduce the trustworthiness of the network. Some consensus algorithms just can't avoid forking due to network latency and miner behavior. And this can even allow for a double spend attack to be launched. Also, hard forks are what are the real troublemakers. They can actually rewrite the blockchain and they can make previously valid blocks invalid, or vice versa. They can make invalid blocks valid. And another aspect of governance of a consensus algorithm are software upgrades, or how the algorithm itself is updated. The algorithm needs to be updated from time to time to make security changes, add new features, fix bugs, or make performance improvements. My final evaluation criteria is compliance. So the first generation of consensus protocols was used as a way to get around government regulation and compliance issues using pseudonymity and confidentiality. But today, as governments around the world are starting to look into using blockchain and implementing their own regulations, it's important that the next generation of consensus algorithms look at these compliance-related features of the blockchain. So two primary regulatory requirements are called KYC and AML. KYC stands for Know Your Customer, and it requires financial institutions to verify certain aspects of a user. AML stands for Anti-Money Laundering, and AML, in conjunction with other fraud detection systems, require the ability to monitor all of the transactions happening on the network and to query the history of the transactions. So a good consensus algorithm should be able to exert control over user accounts to allow requirement satisfaction for KYC, and it should have features that allow for the transparent distribution of transactions on the network to satisfy AML requirements. Secondly, removing illegal content from the blockchain is also important. Now, I know blockchains are built on the premise of immutability, and therefore it becomes impossible for the blockchains to remove content. However, there's been several instances where illegal content has been stored on public blockchains, such as the Bitcoin network. And right now, removing this content violates the principle of immutability, but a good consensus algorithm should provide a legitimate mechanism for the nodes to reach consensus to alter the blockchain in a controlled and a transparent manner. So now I present my framework. So the primary reason for using a blockchain in a business application is the trust and the security that comes with decentralization. Therefore, this model assigns most of the weightage to security and decentralization requirements alone. Also, we've seen a lot of initial deployments of applications based on early proof of work systems suffer due to their lack of scalability or governance models. For that reason, scalability and governance are given the next biggest weights. Furthermore, some governments have issued bans on blockchains because they weren't following certain regulatory compliance requirements. This model emphasizes the importance of these requirements in today's blockchain systems by assigning nearly half of the weightage to considerations related to scalability, governance, and compliance. And by balancing scalability, governance, and compliance requirements with security and decentralization requirements, this model is able to achieve a holistic evaluation framework. So the weights provided in this table on the right are from my paper, and they're based on the analysis of the most common use cases of blockchains today. So based on the application that runs on the blockchain, the user can assign their appropriate weights to each of the evaluation criteria. And for some applications, Scalability and time to finality might be more important than resistance to double spending attacks would be. Like, for example, today, it doesn't make sense to be running all of the credit card transactions on the Bitcoin network because it would take too long and it would be too inconvenient waiting for several minutes just for the block containing your transaction to be confirmed. Similarly, for other applications, security features might be more important than the speed. For example, this could be an application that registers a deed for the ownership of a house on the blockchain. So based on the application, the framework can be used to update the weights and then calculate a weighted score to determine the best consensus algorithm for their given application. So this framework still has its limitations. It is still generic and it might not work for every business application. But in any event, this framework should be used in conjunction with other considerations that could possibly affect the business application being developed. I also recommend creating an open sourced and automated test suite that can run against a target blockchain to help evaluate and generate an automated score for this framework. Thank you so much.